special topic, okay, power quality issues in grid connected PV system. Okay, bersama-sama kita pada petang ni Dr. Jasrul, itu penceramah kita, Dr. Jasrul Jamani Benjamian, itu pengarah ataupun SEDA Certified GCPV Designer, okay, pengarah daripada School of Electrical Engineering, Faculty of Engineering, UTM, Skudai. Okay. Selamat datang kepada semua. Terima kasih kepada semua yang sudah hadir. Okay, kita ada pelajar-pelajar UTHM pun ada. Kita ada staff UTHM. Kita ada sahabat-sahabat dari Politeknik pun ada. Dari Universiti. Okay, Dr. Zul dari UTM pun ada. Terima kasih Dr. Zul. Okay, dan sahabat-sahabat yang dalam satu bidang yang sama, dalam bidang power system dan juga PV. Okay, terima kasih kepada Dr. Jasrul sekali lagi. Okay, sebelum kita mulakan sesi kuliah ataupun perbincangan ataupun webinar kita pada petang ni, kita mulakan dengan bacaan Ummul Kitab Al-Fatihah. Bismillah. Okay. Okay, sebelum tu izinkan saya untuk membaca biografi Dr. Jasrul dulu. Kita punya penceramah kita. Okay, Dr. Jasrul Jamani Jamian received the Bachelor of Electrical Engineering, Master of Electrical Engineering and PhD degree in Electrical Power Engineering from University Technology Malaysia in 2008, 2010 and 2013 respectively. He is currently Director of Power Engineering Division, School of Electrical Engineering, University Technology Malaysia. Dr. Jasrul is actively involved in research as a principal investigator as well as leader in consultancy projects with several companies such as Petronas, Tenaga Nasional Berhad, TNB, which is focused on relay coordination projects and off-grid solar PV design. Okay, I think including grid connected. Okay, he is the author and co-author of more than 80 publications in international journals, proceedings in the area of power systems and energy. Up to now, he has successfully supervised 2 PhD, 1 Master by Research, and 15 Master by Coursework project candidates. His research interests includes network reconfiguration, optimization techniques, and renewable energy. So without further delay, I would like to invite Dr. Jasrul to give a sharing about power quality issue in grid connected GCPV system. Okay.
All right. Thank you, Dr. Muhammad Noor. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, everybody. So before I start, I just would like to confirm, is there any
I think basically we don't have it, if I'm not mistaken.
We don't have
but we have
okay.
But we have Dr. Dul. I think
we have an international staff. Okay. So I will use English 100%. All right. Okay. First of all, I would like to thanks to Dr. Muhammad Noor for inviting me to give a sharing session with all of you about the power quality issue in grid connected PV, GCPV system. I won't go very detailed on power quality, but I will touch a little bit about the power quality that might be faced by all of us when we have a GCPV system. All right, so this is the topic. And just a little bit about myself, okay? So like Dr. Muhammad Noor said, currently actually I'm the director in Electrical Power Division, School of Electrical Engineering. And in the same time, I also a director for the research and development for our spin-off company, which is Sustainable and Engineering Sdn Bhd. Okay, so this is the thing that Dr. Muhammad Noor shared just now. Actually, I got the certificate of competency on GCPV as well as off-grid OGPV. A little bit background about our company. So our company also do some consultation project related to power system study, related to protection relay coordination, solar PV design, including OGPV and GCPV. And today I will share more toward the GCPV, the problem that we are facing previously. So we will share with all of you. We also do some consultation project on lightning protection, electrical competent engineer visiting, as well as electrical power design. And in the same time, also our company do a lot of training related to our you are feel free to interrupt me. Okay, you no need to wait until at the end of the seminar. Okay, you can just interrupt me if you have any question. Just let me know, and after that we will discuss. All right. So the first part I will talk about just a little bit overview about the traditional and modern power system. What is the difference between our previous power system and our current power system? And after that, we will discuss a little bit on PV characteristic. Why PV is a little bit different than our traditional power plant. Why it is quite difficult, or we can say that why it is a little bit important to do a further analysis when we want to connect a huge PV to the grid. The third part, I will discuss about just overview what is a power quality. And last but not least, we will discuss about power quality issue in GCPV. All right. So the first part about overview of traditional and our modern power system. This is what we have in our traditional power system. Normally, how we get the electricity, we get from the generation. Okay, so we can divide into 6 parts. So start from the generation, and after that it will transmit. We will have a substation. The purpose of the substation just for the step up or step down the voltage. Okay, normally it's a step up here, and we will transfer that energy throughout the transmission line, and after that we will step down, go to the distribution line, and lastly go to the demand. Our traditional power system, the energy must come from the generation part. So in other words, it's only one direction from the left to the right, and it's quite simple actually in our traditional power system. So there is no generation have been done at the demand side. Most of the generation must come from the generation side, and after that we transfer through the transmission as well as distribution. So this is what happened in our previous power system. Okay, so we have a protection for the distribution side. Normally is simpler than transmission, because since the direction is only come from the substation to the load. All right. And how we get, how we get or where we get our electricity. Okay, this is the part of the generation. This is the current electricity generation for Malaysia since 1990 up to 2018. So you can see that here during 1990, okay, the total energy is only around 25,000 gigawatt hour, but nowadays we have nearly 175,000 gigawatt hour. And you can see the distribution, or the what we can say that the contribution of the resources. We can say that most of our electricity is come from the coal and come from the natural gas until today. Okay, this data actually I get from the IEA. So the latest data is 2018, and you can see that here most of our electricity actually come from the coal as well as natural gas. Okay, so if you talk about CO2 emission and so on and so forth, of course, coal and natural gas, they are producing a lot of greenhouse effect. And we have our hydro, and we can see that there is a quite huge improvement or quite huge contribution on the hydro percentage since 2014 here. Okay, nowadays, but the percentage of the hydro is still very small. And this yellow part, at the bottom yellow part, is actually our solar. Okay, so for the solar PV, when I take the solar PV, so you can see that during 1990, actually there is no project on solar PV, and we begin around 2007. Okay, 2007 it started to grow, and after that there is a huge jump. Okay, for the solar PV since 2012, and nowadays we have a 573 gigawatt hour. Okay, so this is the amount of solar PV that we have today. Okay, so I believe that the numbers is increasing for 2020 because we just finished our net energy metering. So there will be huge jump as well from 2018 until 2020. Okay, we can see this data on 2022 later. All right. So even though we can see there's a huge amount of percentage, but actually the contribution of the solar still very less, because this is only the part of the solar, this yellow part, if we compare to other resources. All right. So if you talk about the renewable energy, which is a non-combustion renewable energy, this is the solar 573 gigawatt hour. If you compare to hydro, they have a bigger portion on the renewable energy in Malaysia. Okay, so roughly this where we get our electricity. All right. So in summary, I can say that our electricity nowadays, based on 2018 data, actually 45.4% electricity come from the coal power plant, 37.6% come from the gas fired, 15% come from the hydro, and our solar PV is only 0.34%. Okay, even though the number is look like very big, which is a 573 gigawatt hour, but actually it's only contribute 0.34% in our power system. Okay, so roughly this is the overview about our our electricity generation currently in Malaysia. Okay, so what before we go to the discussion on power quality, I would like to touch a little bit the difference between our normal traditional power plant, which is coal, hydro, and gas fired, versus solar. Okay, the major difference between these two generation power plant, our normal traditional, okay, our traditional power plant, actually they are producing AC power. Okay, they are producing AC voltage, they are producing AC current. In other words, they are producing a AC power. However, our PV is actually, they are producing a DC. It's a DC source power plant. Okay, so it's a little bit different than our traditional power plant. Okay, previously, why AC become very popular in the worldwide? Because most of the generation is come from AC. Okay, the coal power plant is AC, the gas fired is AC, our hydro also in AC. That's why AC become dominant in worldwide. But nowadays, when we go to the solar, actually solar PV is a DC power plant. It's not an AC. So if our solar is a DC power plant, so when we want to connect our PV solar to our home or to the substation, we know that our home using an AC supply, our substation also using AC supply, so we need to have an additional component, isn't it? Because you cannot connect directly a DC source to the AC load. Okay, previously here, in this case, there's no big problem because we got the transformer. The transformer will help to step down the voltage, and after that we can connect to our house, we can connect to the substation, we can connect to anything, equipment which is related to the AC. However, since our solar is a DC, we cannot connect directly between the DC and AC. And of course, we cannot use a transformer. Okay, because the basic principle of the transformer is operating in AC. It must operate in AC. If not, the transformer will be saturated. So in other words, if we have a DC source, in order to connect with the AC, we required an inverter. So that's why inverter will come in the PV system. It is compulsory because what inverter will do, it will convert whatever the DC supply from the PV, it will convert to become AC before we can connect to the AC load. Okay, we can connect, either we connect with the our house or substation and so on and so forth. So in PV farm, if you can visit the PV farm, you will see a lot of inverter. Okay, and today we will discuss about the grid tie inverter. Okay, so grid tie inverter so means that it is actually is integrated. You will connect with the grid before they supply to the consumer. All right, so that's what happened since we got the PV, we got the inverter. So what happened nowadays? Okay, nowadays in modern power system, if previous traditional power system, there is only one flow of energy from the generation to the load. Since we got the PV, and this PV can be integrated, can be put at the distribution side at our house and so on and so forth. So what will happen? Our modern power system become what we call it as an active power system. What means by active power system? If you see, for example, in this part, okay, they might have a two direction of power flow. The power can come from the generation to the demand, or the power also can flow from the demand to the generation part. Not to the generation, means that to the grid or to the distribution system. So if previously the system must flow from the generation, okay, here must flow from the generation to the demand. Nowadays the demand itself, they are able to generate electricity. So that's why we can see that on the pattern for the modern power system, there's a lot of two-way power flow. Okay, two ways of direction of energy flow in the distribution system. Okay, so it's a little bit different. So there are actually there are a lot of issues in terms of power system. Either the system able to cater the demand or not, to cater the bi-direction of power flow in terms of protection. If let's say we got a directional power, directional overcurrent relay, what will happen to this system and so on and so forth. But that one actually in the different topic. Okay, there's still a lot of research that have been done or still ongoing on this when we have an active distribution network, when we connect our renewable energy to the distribution side. But for today, what you need to know, for modern power system, currently we will have the distribution network might generate electricity for their own use, or they also can export this energy to the transmission level. Okay, so that's the first part about the overview for the our traditional power system versus the modern power system. Okay, the second part I will discuss on PV characteristic, why PV is different than traditional power system, and why it is very important for us to take care about it. All right. So this is our traditional power system. Like I told you just now, I just take one example of the hydro power plant. So if you see on the hydro power plant, so what we did, we got the dam here, and after that from the water flow, it will turn the turbine, and after that it will generate electricity, go to the power line, isn't it? So this is how our power plant, hydro power plant works. And we have a control system. We have very good control system here, which is our control gate. If we want to generate more power, what we need to do, we just need to open wider the control gate to make sure that there's a lot of water flow to the turbine. Automatically we can generate more electricity. If we want to make it, if we want to reduce the amount of energy, okay, to be generated, so what we can do, we can control the gate, we can close the gate. If we close the gate, automatically there's no electricity will be generated. Or if we just open 20% of the gate, so indirectly we only produce 20% of energy. So the gate, the control gate here will play an important role for the hydropower plant. If we said about the fuel power plant, or we call it, for example, like gas turbine and so on and so forth, the gas turbine, we control the fuel here. Okay, if we want, for example, let's say the demand increase, okay, suddenly there's a demand increase, what we will do, what the power plant will do, they will inject more fuel. When they inject more fuel, there will be huge combustion, and automatically they will produce more power. Okay, because this combustion will produce a high, very high temperature, and after that, that temperature air will turn the turbine, and from the turn the turbine, it will turn the generator, and produce electricity. So In other words, for our normal gas turbine, okay, or we call it a thermal power plant, we can control the injection fuel to the generator, okay, to the generator. In other words, we can control easily the output of the generator. Same goes to the hydro. Okay, for the coal, for example, we also can easily control the output of the coal power plant by controlling the amount of coal that will be burned inside the boiler. Okay, if let's say you want to have a huge power, so what you need to do, you just need to put more coal inside the boiler, so it will produce more steam, and from there you will turn the faster the turbine, so it will generate more electricity. So based on our these three kind of power plant, is quite simple to control. It's not simple, but it can be controlled for their output. So you can control either you want to have a huge amount of energy or you want to have a less amount of energy. But it's a little bit different than PV. Okay, if we have a PV, definitely we know that the PV is come from the sunlight. Okay, they require the irradiance. When the irradiance reach to the cell on the PV module, what will happen? It will produce electricity. So the first disadvantage or the first constraint on the PV system, we cannot control the sun, isn't it? You cannot put the sun. Okay, okay, sun, please be at this position for 5 hours, for 7 hours, and so on and so forth. So, in other words, we cannot control the electricity generation from the PV panel. Second, we cannot control the irradiance. Okay, these are some example of the irradiance that we measured at the PD on 8 October 2020. And you can see that the irradiance itself actually being influenced by many factors. Okay, one is in terms of the sunlight irradiance itself. Second, actually, it also being influenced by the cloud movement. For example, at this moment, if you see maybe around 12 something, maybe there is a cloudy at this area. That's why suddenly the irradiance value is drop. So in other words, the first thing, we cannot control the sun itself. The second, we cannot control the irradiance that reach to the PV panel because it might be disturbed by the cloud movement and so on and so forth. So in other words, you can see that you cannot know, actually, you cannot predict how much the energy that can be generated by the PV module. Okay, so this is the real pattern that we collect on 8 October 2020. So in the morning, you can see that the irradiance is quite low. They goes a little bit high during the afternoon around 11, but after that there's a cloudy. Okay, there's a cloud movement and so on and so forth. So it's drop, quite huge drop, and after that during the afternoon it will start to increase back and reduce until to the night. So this is the second disadvantage on the PV module. We cannot control the sun. We cannot control the irradiance that can reach to the PV module. The third one, we cannot control the injected power. Okay, for example, I just take one of the sample of the PV module. In this PV module, assuming that there is a label of the PV module and it's stated here 30 watt. Okay, we need to understand that this 30 watt, we can obtain this 30 watt if we have irradiance 1000 watt per meter square. Okay, you can only reach this 30 watt if you have 1000 watt per meter square. And from this irradiance pattern, for example, that I took on 8 October at the Port Dickson, this is 1000 watt per meter square. You can see that it is only at certain time that it reach 1000 watt per meter square. And most of the time, the irradiance is lower than that. So in other words, even though you already put 1000 watt PV, it's not necessary you got 1000 because it's depend on the irradiance. So in other words, if you do a measurement, of course, at this moment, at this part, actually the total power, if you are using a this 30 watt, is maybe less than that. If 600, maybe it's only 15 watt, 10 watt, 18 watt, 17 watt. Here you got 30 watt. So we cannot control the sun movement, we cannot control the irradiance reach to the PV module, and the third one, we cannot control the injected power. So you can imagine that, okay, you can assume that, let's say if you got the system, this is your system, and you inject with this PV farm, and this PV farm, the injected power to the grid is uncontrollable. Okay, you cannot control. Okay, because based on this waveform, so it's not necessary, you will not produce 30 watt, sometimes it's produce 15 watt, maybe less than that, sometimes higher than that. For example, here, since the irradiance reach 1200 watt, so in other words, you will be higher than 30 watt. So we can conclude that we have an uncontrollable energy injected to our power system when we use a PV. So it's a little bit different than hydro, coal, as well as gas fired. Okay, for the hydro, coal, and gas fired, we can control the amount of injected fuel. Indirectly, we can control the amount of power that to be injected to the grid. But in this case, we cannot control the sun, we cannot control the irradiance, so we cannot control the energy that will be injected to the grid. So due to this problem, there might cause some power quality problem in our power system. All right. So I will touch a little bit about what is a power quality. So just overview of the power quality. So what is the definition? What is a power quality? The term power quality is used to describe the extent of variation of the voltage, current, and frequency to the power system. In other words, we can say something like this. Uh, if we have poor power quality, indirectly, we will have a problem in terms of voltage. We might have a problem in terms of current. We might have a problem in terms of frequency. Okay, a good power quality system means that we have a good voltage, good current, and good frequency. So the variation of this voltage and current, okay, it can be either in terms of magnitude or it can be in terms of the shape. Okay, the shape also being distorted due to the low power quality. So this is some several power quality problem that you can see. Not necessarily on solar, but actually is on our normal power system. So this is the list of the power quality problem. Okay, the first one here is actually is due to the power factor. Okay, we got a power factor problem. Here is actually is a under or over voltage problem. Here is a harmonic problem. Here is a flicker problem. Here is a voltage unbalance problem, the sag problem, voltage dip and swell problem, voltage transient, voltage interruption, as well as a frequency deviation. Okay, so this is some of the power quality that I think maybe you have learned in your class. We will not touch all of them. Okay, I will discuss only some of them which is related to PV. All right, so let's discuss some of the power quality problem. First, we are talking about under voltage. So what means by under voltage means that we know that our power system under TMB regulation, the voltage for the low voltage is a 230 volt, isn't it? And we got the range plus minus plus 10% and minus 6%. Okay, sorry, I'm using my mouse. Okay, so we got a 230 plus 10% minus 6%. As long as this voltage between this range actually is a good power quality. Okay, but when we talk about under voltage, we are talking about the voltage value which is lower than minus 6%, and it has happened around 1 minute. Okay, there is a time frame. Okay, so if the time frame it is longer than 1 minute, so we declare it as a under voltage condition. So if let's say your voltage level is still within this range, we are not we won't say this value as an under voltage. The under voltage means that it must below than minus 6%, not 6 volt. Okay, minus 6% from the 230 volt. So in this case, we can see that, okay, this is some example. This is the normal voltage, and suddenly you have this voltage. Okay, so this voltage we can call it as a under voltage. Okay, As long as it is less than -6%, we declare it under voltage. So why under voltage can happen? Actually, it might due to the too long of the wiring system or insufficient size of the wiring system. And this is very important when we talk about the solar, either GCPV or off-grid system. Because normally people, they just take for granted about the distance of the wiring. Okay, if you have a longer wiring for your PV system, automatically there will be huge voltage drop. In other words, you will face under voltage problem. Okay, that might be one of the reason of the under voltage. The second reason might due to the poor voltage regulation on the system level. The third one might be the loose connection, and the fourth one is might due to the overloading circuit. Okay, why overloading circuit can cause under voltage? Because when you overload your circuit, actually there's a huge current that flow throughout your wiring. Okay, so in other words, the voltage drop become bigger. Automatically, the voltage at the terminal will be lower. Okay, so roughly that's the idea why under voltage can happen. So under voltage is one of the power quality problem that we might face on the GCPV system. Okay, the second one is over voltage.
Can I interrupt, please?
Yeah, sure. Please, doctor.
Okay. Assalamualaikum warahmatullahi wabarakatuh. I have two questions.
Yeah,
One
doctor.
is regarding you use the word active in terms of the double way power flow, two-way power flow.
Okay, yeah.
You use the word active. You use the word active.
Active.
Means, yeah, normally passive we say whenever we consume it. Is that passive?
That's right.
But whenever we generate any component is generating, it is known as active, like amplifiers.
That's right.
Is that so? You use the term active. So it is
Okay.
in terms of the any definition in power quality, or it is from your side? That is my
Okay.
first question.
All right. For that one, actually, when we talk about active, I'm actually referring to the distribution network behavior itself. If previously our distribution network is only consume the energy, there is no energy being supplied by the distribution, isn't it?
Doctor, I mean that the word you use from your side, or it comes into the power quality definition, means it is
It's
standard.
it is a active distribution network is a normal term.
Okay, clear. Okay, now
Okay.
second
Yeah.
question.
All right.
Second question, because you know this the power quality issue is just 2-3 decades is the old is here.
That's right.
So day to day their definitions are changing.
I'm agree with you.
Therefore, yeah, therefore definition. Therefore, it was not clear to me. Therefore, I just asked you whether it comes into the definition of the power quality or not. So if it is coming, means maybe any research coming or any book standard code book is coming. So they will put this definition also.
Okay, actually, we got the definition for, we have a standard that define the power quality, but I did not go very detail on it. But in general, we can say that the definition of the power quality is any variation of the voltage, current, and frequency due to our demand or due to our generation. So that's that we can define as a power quality.
Okay, that means that is your guess. That is your guess, not in terms of any standard defined by the standard definitions.
Actually, there is a standard. The standard
Okay.
also reflecting to this definition.
Okay, thanks. Okay, thanks.
All right.
Next question is that just now you told about this. You are talking about the under voltage.
That's
Very
right.
good. Your explanation is very good. But just my is that you referred that Malaysian standard for distribution +10 -6.
That's right.
Is that so?
Yeah, yeah.
In terms of the power quality, is there any standard that is defined by IEEE the power quality for the TNB? Because until now we are whatever we are referring IEEE system or any not NSI but IEEE we are using, that is standard we are referring in our academic. If there is any kind of the book is there or any TNB any guide is there, that can you please share later on if it is the standard is there?
Okay. About the range actually have been carried out by our Energy Commission, which is Suruhanjaya Tenaga Energy Commission. So inside the Energy Commission, they have stated the standard of the variation that they allowed, which is +10 and -6%. Okay, but yeah, I agree with you. IEEE have their own range. Even some countries have their own range. Some of them they got the +5, -6. Some of them got the +6, -10. Some of it +10 and -10, and so on and so forth. Uh, but by definition, the under voltage is whatever the voltage below than the acceptable range. So it's up to the country. If the country say, let's say the country, the range that they allow is -10%, means that the under voltage for that particular country is below than that -10%.
Yes.
Okay, Doctor?
Yes, I agree with that one. Actually, my meaning was that if there is, suppose we are referring the Malaysian standard, whether
That's
it is
right.
TNB or IPP, whatever is there,
Mm-hmm.
so we have to follow those standards that in our education system, because I have taught this subject many times, so
All
we are
right.
referring IEEE. We don't have
Okay.
any code from the TNB.
Actually, you
So,
can quote from the TNB. TNB actually they are referring to the Suruhanjaya Tenaga, which is our
Suraj,
energy.
oh, now you told me
Yeah.
that now next time if I get opportunity, I will follow that one. Now the
Okay.
question from that question another is coming. Will you touch to the transmission system also? Because you are going to connect grid connected is there. So you will
Yeah,
be limit to the
but
distribution
this
only or going.
discussion did not go until transmission level.
Okay, good. Okay, okay. Thank you very much.
All
Okay,
right.
thank you.
Okay, thank you, Doctor. All right. So next, we are talking about the over voltage. Okay. For the over voltage, they might happen due to the power regulation of the power source or power quality. Sorry, power utility company. If let's say we got a poor regulation at the distribution side, so what will happen? We might have an over voltage problem, or we have a reactive power imbalance. Okay, we will discuss this one when I show you some case study at the next slide. Okay, so in other words, there might have a two problem that cause over voltage. One is might due to the poor regulation itself. The second one might due to the reactive power imbalance. Okay, so next, harmonic. Okay, normally people talk about power quality, they are referring to the harmonic. Okay, so what is a harmonic? Actually, this the example of the pattern of the harmonic. The red line here is actually our normal, our pure sine wave waveform. And after that, let's say we got this, the green, okay, the green one is a fifth harmonic waveform. The blue one here is a third harmonic waveform. And when you combine the red plus blue plus this green, and this is our actual waveform that we obtain. So this is the actual current that we might obtain if we have a harmonic in our system. Okay, so you can see if you compare between this black one and this the red one, the harmonic, okay, the waveform have been distorted. Okay, so this is an example of the harmonic problem that we might face if it's become one of the major issue when we connect a PV later. So where's this harmonic come? Actually, it's come from the nonlinear load. Okay, for example, if we have a variable frequency drive, okay, we have a motor, for example, and after that we want to control the inrush current for that motor. We want to use a VFD. So what will happen? Actually, it will contribute to the harmonic. Or if we have an uninterruptible power supply, also it can become one of the injection to the harmonic. If we got the fluorescent light, if we got the computer, or even if we got the inverter. Okay, if you still remember, I have mentioned to you that when we have a PV, we must have an inverter. So actually this inverter also will give some contribution. It will inject harmonic to the system. Okay, but how serious it is, we will see later. Okay, the third one is in terms of power quality problem is in terms of voltage imbalance. Okay, voltage imbalance also one of the power quality problem. So what means by voltage imbalance? Let's say you got a three phase and one of the phase, the voltage is higher than the others. Okay, so this is the voltage imbalance problem. So normally we will see this kind of problem if we have a large single phase load. Let's say you got a three phase, but one of the phases they have a larger single phase load, or for the household, for example, let's say you are using a three-phase, but after that you are not properly distribute all this single phase. So what will happen? We will have a voltage unbalance. Okay. And last but not least, about in terms of power factor problem also one of the power quality problem. So why power factor problem can happen? Actually, might due to the high inductive load as well as real power injection. Okay, in this case, the second part we will discuss in terms of solar. Why suddenly the solar PV can disturb, can influence, can give an impact to the power factor problem. All right. So we go to the last part, okay, which is power quality issues in the grid connected PV. So this is some example of the under voltage problem. Okay, this is the real problem that we face. Okay, one of the project in the northern part, northern Malaysia. So we have a very huge PV here. Okay, this is our protection system and so on and so forth, and this is our MPPT. The distance between this MPPT go to the building is nearly 300 meter. And what happened, because they are wrongly sized the cable, the voltage drop is very high, which is 7%. Since the voltage drop is very high, in other words, it is less than minimum value that being given by the ST. So you can imagine that if this our MPPT producing 400 volt, automatically whatever the load at the end of the site is a minus 7%. Okay, if you still remember our ST, Suruhanjaya Tenaga, or our energy commission, their standard is only minus 6%. So for this case, what will happen if we facing this problem? If we wrongly design the cable size, we will have a under voltage at the load terminal. So we need to make sure that we do a proper sizing on the on the cable, so that we get less voltage drop. Automatically, we can make sure that our voltage within the limit. So this is one example of the under voltage phenomena that might happen when we have a GCPV, okay, grid connected PV system. So the second is about the over voltage. Okay, for example, let's say this is our distribution system. We got the load 1, load 2, load 3, and load 4. Okay, this one is more through the simulation because I don't have the actual data. Okay, let's say without this PV, okay, without the PV farm, this is the pattern of the PV, of the voltage that we will obtain. Okay, here from the bus 1, we got a 1.017, and at the end, bus 4, we might have a 0.997. In this case, we can say that all the voltage are within the acceptable limit. If you still remember, plus 10, minus 6, isn't it? In this case, it's only minus 0.003%. 0.003, or in other words, 0.3%. Okay, so this is the range that we have without the PV. And what happened if suddenly we inject PV at the end of the bus? Okay, because it's a distribution, isn't it? So this is the voltage pattern that we have. Okay, I put it in the 4 cases. Okay, case A, case B, case C, case D. The higher the PV size, or the higher the energy that being injected by the PV, the voltage at the end of the terminal will increase. Okay, so you can see that here is a 0.0997, and after that they might increase until 1.05, which is 5% than the normal standard value. Okay, but it's still within the limit. But you can imagine if you have a larger power, so a larger energy to be injected, so you might have a larger voltage at the terminal. So you might facing a over voltage problem. That's the first case. The second, like I told you, since we cannot control our energy, isn't it? For example, like in this pattern, we cannot control the energy. In other words, the voltage at the bus 4, bus 3, bus 2, as well as bus 1. Bus 1 maybe not really affected because it's very close to the substation. But for the bus 2, bus 3, and bus 4, you can imagine that the voltage will fluctuate it depends on your amount of energy that being generated. So in terms of design, we need to make sure that, okay, in terms of design, we need to make sure that based on the worst case, means the largest energy that might be injected by the PV, you need to make sure that the voltage will not exceed the limit, the over voltage limit. If not, you might have a problem. For example, let's say you use auto tap, okay, auto tap transformer. Let's say initially the voltage here is very low, so you tap the transformer to improve the voltage. What will happen if suddenly you got a huge power from the PV, the voltage might beyond the limit and cause over voltage. Okay, so this the phenomena over voltage that might happen when we have a PV injected to the system. Okay, the third case just now we discussed about the harmonic. Okay, in terms of harmonic, actually we have not really, we don't
One
have
question,
any
please, here.
big. Yeah,
Doctor,
yeah,
one
sure.
question. Doctor, did you consider temperature? You consider the length of the conductor. Did you consider the temperature also that affect the voltage drop?
Of course.
Environment.
Yeah, I agree with you. The temperature actually will influence the voltage drop, but the most significant voltage drop is due to the current, isn't it? So the temperature we can consider as well, and it will give a worse case. It will give a higher voltage drop rather than the normal temperature. So if we consider the temperature, let's say we got the bare conductor, we have a conductor without any proper insulation. So what we might have problem, the voltage drop will increase, and in other words, the under voltage phenomena will happen frequently rather than if you have a proper conduit for the cable. Okay, doctor?
Okay, thank you.
Yeah, I agree with you. Of course, the voltage drop will also be influenced by the temperature because the temperature will affect the resistance of the cable and indirectly will affect the voltage drop. Okay.
Therefore, my question was that you consider only length or both you consider. Therefore, that's my question.
Currently, I'm not considering the temperature, but actually the temperature will give an impact.
Yeah. Okay,
Yeah.
thank you. Thanks.
Okay. The fourth one, in terms of harmonic, actually the inverter, the grid tied inverter also will produce harmonic. Why they produce harmonic? Because they're changing from the DC to AC, isn't it? So when we have a switching, automatically it will contribute to the harmonic. And if you see, this is one example of the grid tied data sheet, and you can see that the maximum total harmonic distortion normally is less than 3%. So in terms of harmonic, the value is not very big. The value is very small, okay? But can you imagine when you have a multiple inverter and each of inverter also contribute to the harmonic, it might give a huge impact as well. Okay, for example, in this case, we got the grid. Okay, the grid is they give a pure sine wave, and after that we got this AC load, we got the UPS, we got whatever the load that contribute to the harmonic. So this harmonic will be injected to the bus bar, and in the same time we also have a grid type inverter that also contribute to the harmonic. So by definition, if you are looking on the single component, the grid type inverter, the harmonic is very low. It's less than 3%. But the combination of it, they might give a quite huge harmonic. So the standard, they recommend that if, let's say, your load is a very sensitive load, you still need to do some monitoring on the harmonic after you injected, if after you integrate your PV to your system, to your network. So that what being suggested. Okay. By definition, if you see, if you go to the data sheet, yeah, it shows that it's very less. Maybe the percentage is not very huge, but remember, you are integrated with others load. This 3% or maybe 2% also will give a huge impact to the system. Okay. And the next one, okay, this one, sorry, the title, there's a mismatch on the title. Okay, actually it's a voltage imbalance. Okay, for those who are using three-phase system for your house, just for your information, normally our house, even though we are using a three-phase system, normally all these phase, each phase will be distributed, okay, to a different location. For example, maybe red phase go to the kitchen, the yellow phase go to the main hall, the blue phase go to the second floor, for example. Okay, so in other words, we might have a three-phase supply from the TMB, but after that our load is still single phase, and they are being distributed to a different area. So since we have this kind of connection, what will happen actually, we might have a voltage imbalance in most of the cases. Why? Because for example, let's say we are not using any load at the second level, automatically the voltage is higher than the others. That's the first case. And let's say if you put a solar, you inject a solar PV, and this solar PV only single phase. Okay, so what happened to the system? Suddenly they will have an injected power from the PV, and indirectly it will also cause a voltage imbalance. So it is recommended that if you are using a three-phase for your house, make sure that you are using three-phase inverter as well, so that the power that being injected by the PV will be equally distributed for each phases. Okay, so try to avoid your house using a three-phase system, three-phase meter. Okay, even though actually it's a single-phase load, but after that you connect with the single-phase PV. Okay, if you are using this condition, it will make the voltage imbalance become worse. All right, and last but not least, this is the most critical part, the most significant impact that we can see when we inject PV to the system. Okay, the PV can cause power factor problem. This is the real power factor measurement that been taken from the TMB for the transformer. The blue line before we have a PV, and the dotted line when we have a PV. And you can see here, start from the afternoon is around maybe 10:30 until 4:30 will drop significantly. Okay, previously the power factor around 0.96, but now is less than 0.9 during the noon. Okay, what happened actually, this is the phenomena. I will explain to you why this condition can happen. Let's say our normal factory, we got the TMB, we got the meter. So the TMB will supply P and Q, and the meter will transfer the P and Q to the our factory, isn't it? So from this P and Q, we will have this P, we will have this Q, and this is our theta. Okay, so this is the original without any PV. And suddenly, let's say you got the PV. What will happen? The P load still same. We are still using a same P, okay, which is a P load, the same factory. We are not add up a new load. So with the same P, with the same Q, but the P will be can come from the TMB itself as well as from the PV. So as you know, conservation of energy, whatever the energy required by the demand must be equal to the power come from the source. So in this case, what will happen, if you see this graph, okay, let me use, okay, this is come from the TMB. Previously, the TMB supplied the whole line from here to here previously, but now they only supply this much of amount of P. Why? Because some of it being supplied by the PV. But remember, our previous, okay, last 3-4 years, most of the inverter, the power factor is 1.0. So the PV did not inject any Q. So the P real power from the TMB is lesser, but the reactive power still remain the same. Why? Because whatever the load still remain the same, isn't it? So The supply P from the TNB is reducing, but the Q still remain the same. And you can see this is our previous theta. This is our new theta. So what happened? There are few cases, the factory when they put the PV, yeah, we agree that the bill, electricity bill is reduced, but the total bill is same. Why? Because they get the penalty due to the power factor correction, due to the power factor problem. So this is one of the power quality problem, the major problem that we might face if we install PV, if we use inverter with power factor 1.0. Due to this problem, okay, due to this problem, ST, they already come out with the standard, all inverter must able to provide reactive power as well. Okay, if I'm not mistaken, last 2 years, they come out with the standard, it must be at least 0.9, and the latest now, the current latest inverter, for example, this inverter, they can provide up to 0.8 lagging and leading. So in other words, they can provide, it not only provide P, but it also provide Q. But we still need to very careful. Sometimes even they able to provide Q, but if the Q is not enough, the factory might got power factor penalty as well. So there are few cases that I have experienced. So we need to install external capacitor bank to support the PV. Okay, so that the factory or the industrial will not being penalty by the TMB due to the low power factor. So I think that's all about my presentation. So in overall, what we can see that when we have a PV injected to the grid, we might have an under voltage problem, okay, due to the wrongly designed in terms of cabling. Okay, we might have an over voltage problem, especially during the afternoon if our demand is very low and our generation is very high because of the afternoon, isn't it? During that time, actually, we can have a over voltage problem, and we might have a harmonic problem. Yeah, I agree that the harmonic from the inverter is very less. It's around 3%. It's less than 3%, but the combination of this 3% might cause a big problem on overall system. Okay, and we might have a unbalanced, especially when you have a three-phase system and you only inject single-phase PV to your network. Okay, and last but not least, the most critical one is in terms of power factor. In the real case study, the transformer load profile shows that the power factor drops significantly when we have a PV, because PV, their main task, actually they generate real power. Okay, the reactive power actually being controlled by the inverter, not the PV. The PV itself, they only generate the real power. When we have an inverter, the inverter try to control the reactive power, but it's still limited up to certain level. So in other words, you might require additional capacitor bank to support the system. Okay, so I think that's all for my sharing session. If you have any question, feel free to ask.
Doctor, the second
Yeah.
last slide. Second last slide. This is
Second
3%.
last slide.
3%.
Okay,
3%
this
of
one.
the harmonic. Yeah, 3%. Less
Yeah.
than 3%. This is actually from manufacturer. It is from manufacturer because you said it is provided by the this whatever we are putting the grid. That is the
Yeah.
PV grid. Is
This
it?
this is
It is,
this is
yeah,
the
inverter.
inverter.
Inverter. So it varies from company to company and rating to rating.
Yeah, it varies from the one brand to another brand.
Yeah, because last time we attended ABB this session over here in
Yeah.
UTHM, in
Okay.
UTHM. So I think his brother was working. One of our student, his brother was working there. So he given the talk. and he said that ABB has that's very good that they don't have this harmonic problem. Means their
Oh.
brand is so good, yeah, their the quality is so good that the
Mm-hmm.
ABB is providing that the pure like the distortionless, like you can say,
Okay,
harmonicless.
what I can give a comment on that. Actually, they got the harmonic, but
Uh,
inside the component, actually they got a good filtering system.
yeah, you're right.
Because the harmonic must be there because there is a switching from the DC to AC.
Yeah.
Whatever the switching condition will cause there is a harmonic exist. But some brand they are not filtering everything. You
Oh,
know, if they need to filtering everything, in other words, you need to have very huge filter, isn't it? And this huge filter automatically will give a cost to the inverter itself. So that's why some company, okay, some brand, they just limited up to 3% because based on our regulation, we cannot inject huge harmonic. So they try to reduce, but they not make it zero. In your case, maybe the ABB, they try to promote means a zero harmonic. In other words, actually they put a bigger filtering inside the inverter so that it will produce a zero harmonic. But I believe that the cost may be a little bit expensive because they have an additional size of the filtering.
you're very right. You're very
Yeah,
right. So
because
payback
because
period,
because we
pay,
because we
yeah,
convert from the DC to AC, of course there will be a harmonic there. But how big the filter that be included inside the inverter? That's the question.
then will come the question of the payback period.
All right.
Then will be the coming that if the cost of the inverter is so high,
Yeah. Yeah.
then will
Of
the
course.
question again will question will come about the payback period. Are you charge more from the
Yeah.
consumers?
Yeah. I agree with you.
Okay, thanks.
All right.
Okay. Thank you very much, Dr. Jasro, for very clear presentation about
Excuse me, doctor.
Yes.
okay, we open question from the participant. Maybe do you have any question? You can ask question to our speaker.
Excuse me, doctor.
Okay, Abdul
Yes,
Rahman,
please.
please.
Yeah. Yeah, doctor. How we can get the record for this section?
Okay. Okay.
Yeah.
Thank
You
you,
you
Abdul
need to
Rahman.
contact the UTHM.
Okay. Okay.
Abdul Rahman,
And also,
actually,
I have a comma that because my FYP was about power quality, the
yeah.
TMB standard is +5 or -5 for low voltage. Means the voltage range around 230 or 430.
Okay.
It's plus.
For the TMB standard, it's actually 230 volt. It's not a
Yeah.
240 volt, and it's a
For,
plus 10% minus 6%. That's the standard that being used by TMB.
because I already checked the data sheet before they was right +5 or -5 for low voltage.
Okay, Abdul Rahman, you need to refer to the ST, Suruhanjaya Tenaga, or Energy Commission Malaysia. That's
Okay.
a standard that being used. The plus minus 5, I believe that one actually they are referring to the some IEEE standard or some literature in the paper. But actually, when we want to refer to the under voltage, we should refer to the voltage range that being given by the country. So each country will have a different voltage range.
Okay. Okay. Thank you, doctor, so much.
Okay, welcome.
Okay. Assalamualaikum.
Okay. Thank you, Abdul Rahman. Okay, any other question from the participants? Lagi
It's okay. You
soalan?
can ask in Malay. If you don't want, if you don't in English, you can ask in Malay.
Boleh tanya dalam bahasa Malaysia. Siapa-siapa ada soalan? Okay, saya tanya Dr. Jasrul lah.
Oh, okay.
Ini soalan simple ya sebenarnya. Dr. Jasrul, let's say dekat rumah kita ada three phase system, three phase electrical wiring. Let's say kalau kita nak install PV, kita nak install single phase. Is it possible ke tak? Is it possible in term of maybe regulation, in term of maybe Malaysia punya regulation? Ataupun mesti install three phase?
Okay, in terms of regulation, actually there is no problem. You can install a single phase PV to your house, even though your house using a three-phase system. But you might facing this problem, which is a unbalanced voltage.
Okay.
Okay. because you connect a single, the idea like this. For example, let's say you are not in the home. You go, okay, all of you go to hometown, your hometown. So there's no load at all. Let's say you switch off everything.
Yeah.
So in other words, we can say that there is no demand. So, but suddenly you got the injected power from the PV during the noon, isn't it? And this injected power go to the single phase, and what will happen? It might cause one of your phase, the voltage might increase higher than the limit. So that might cause the over voltage lah. So that's why we say that it is recommended that if you are using a three-phase system, it's recommended to use a three-phase inverter so that you can balance up if let's say there's an injected power and so on and so forth from the PV. There is no problem. You can use it as single phase because your load also being distributed single phase, isn't it? But it is recommended to use a three-phase so that whatever the power that being injected, it will be equally distributed for each phase.
Okay, all right. Terima kasih, Doktor. So, any other question from the participant?
Hello, Assalamualaikum.
Okay,
saya Aldi Munira. Saya nak tanya soalan simple je lah. So saya nak tanya kalau contohnya macam untuk stand alone punya sistem, kita masukkan charge controller untuk pastikan yang battery bank macam charge correctly macam tu lah kan. Tapi kalau untuk yang grid system, kita tak ada charge controller tapi kita ada MPPT. So saya nak tanya function MPPT tu sama macam
buka kipas kuat sikit.
Dengar tak?
Aircon nak buka-buka lah. Kena on macam ni lah.
Dengar. Saya dengar.
Nak on.
Okay.
So saya nak tanya, function MPPT tu sama macam charge controller ke atau macam mana? Sebab yang saya tahu setakat ni, ada kebanyakan grid system kita tak guna battery bank. Tak perlukan battery bank sebab kita terus hantar dekat TMB, excess energy. So saya, itulah soalan saya. Clear tak?
Okay, clear. Alright, so I will answer in English so that all of you can understand it easily. So the question that being asked by Nur Aini, for the off-grid system, we got the charger controller. And for the charger controller, actually we got the two types, which is PWM as well as MPPT. And this charger controller being used to control energy that being injected from the PV module to the battery. Okay, correct. I totally agree with you. And we got the inverter, and now the inverter for the GCPV, grid connected PV, we don't have any battery. So since we don't have any battery, so what is the difference between MPPT? Okay, what's the difference MPPT in inverter versus MPPT inside the charger controller? All right, so that's the question that being asked by Nur Aini. So actually the answer, MPPT is a technology. Is not related to the charger controller or to the inverter. Okay, the MPPT we can have MPPT technology either on inverter or we can have an MPPT technology on the on the charger controller. The purpose of the MPPT actually, they try the meaning of the MPPT is a maximum power point tracking. So the main function of the MPPT, they try to search the maximum power that they can drag, that can be obtained from the PV module. That's what MPPT do. Okay, so in other words, if let's say you got the inverter, so this is your inverter, okay, you got the PV, so this inverter will try to find, okay, they use a MPPT technology to find what is the maximum power that PV can give, and directly they send to the load. Okay, this is an inverter case for the GCPV. For the charger controller, since charger controller, we have a battery, isn't it? So what they do, they use an MPPT technology, okay, to try to get what is the best, what is the maximum power from the PV, and after that they send it to the battery. So in other words, the MPPT is just a method, is just a technology, is just an algorithm in order to trace the maximum power from the PV and after that send. Either send to the load directly for the case of the inverter, or send it send it to the battery for the charger controller punya concept. Okay, so you might have something like this. You got the charger controller, you got the PV, you got the charger controller, you got the battery, and this battery you connect with the inverter, and this inverter also got the MPPT. You can have this kind of technology, but actually it's useless lah, because you connect directly to the battery. Why you need to use an MPPT inverter? Okay, but most of the time I agree with you. We got the MPPT. But the function of the MPPT in these two cases is a little bit different. The main function is still same, but the operation is different. The function is to get the maximum point from the PV, but for the inverter, directly go to the load for the charger controller so that they can charge maximum power to the battery. Okay, Arni.
Okay, faham, Doktor. Terima kasih.
Okay, sama.
Okay, terima kasih Arni. Okay, ada lagi soalan? Any other question from the participant?
Assalamualaikum, Doktor.
Waalaikumsalam.
My question is it allowable for a grid connected to have battery system?
Yes, actually it's allowed to have a battery system, but it's not cost effective.
Is there any rules or regulation?
Pardon?
Is there any rules or regulation?
No, actually there is no rules or regulation. Actually, we can use a battery for the grid connected system. But the most important thing that you need to know when we want to install a PV, normally we are talking about the cost. How expensive the cost of our PV system to generate electricity. Or in other words, there is a one term, what we call it as cost of COE, cost of electricity. Okay, we don't want to have a system that that is a high cost to generate electricity. If we have that kind of system, it's better we use from the TMB, isn't it? So if let's say you have a grid connected system, but you add up with the battery, it will make the overall cost become expensive, and it will cause the cost of electricity for that particular system become expensive. That's why in general, it's very rare people to use battery when they have a grid connected system. But except for the case if for the factory or industry, that if they are, for example, some industry, they have a two tariff. Tariff during the night is very cheap. Tariff during the morning or during the noon, okay, during the day is very high. If we have this kind of tariff, some technology, they will use a battery so that during the night, they use energy from the TMB, from the utility to charge a battery, so that during the day, they will use two energy. One energy come from the solar, another energy come from the battery to support the system. Okay, that's why actually it is allowable to use a battery, but it depends on the case. Okay, some cases, if you use a battery, it's become very expensive and it's useless. But some cases, if you use a battery, it might help to improve your system. It might help to reduce the electricity cost and so on and so forth. So to answer your question, yes, it is allowed. There is no problem, but you need to be very careful when you want to use it. Okay?
Okay, thank you, Doctor.
All right, welcome.
Okay. Any other question? Maybe last question from the participant, if any. Okay, mungkin tak ada. Okay, so thank you very much, Dr. Jasro, for very clear presentation. Okay, regarding the basic concept of the power system, photovoltaic system, as well as power quality issue in grid connected PV system. I think this is a very good, very nice, very clear presentation that easy to understand. Okay, I think it can give a good benefit for my student. Here we have power quality student. Okay, my student. We have our friends, our lecturer, UTSM lecturer. We have UTM lecturer. We also have lecturer from the Polytechnic, I think, from other institution. Okay, thank you very much, Dr. Jasro. Thank you very much to participant for joining us. on behalf of Faculty of Electrical and Electronic Engineering UTHM, University Tun Sri on Malaysia,